Yes, good morning, Kartika. Good morning. Yes. So, in this class, I'll be talking about this quantum theory or evolution of quantum theory. In the last class, we talked about everything like Abba principle. We talked about like vector atomic models, Z-man effect, anomalous G-man effect. Everything we talked about. Now, in this class, I'll be starting this quantum theory, especially the quantum mechanics. Yes, Ashwin. Good morning. So let's start this quantum theory. So in this class I'll be telling you that how this quantum theory evolved. Okay, how this quantum theory evolved, why we need another theory, because initially we had classical mechanics, why we need quantum mechanics, that I will be telling you in this class. Okay, and everything will be through mathematical, but I won't derive I won't do a lot of derivations, because derivations are not that much important. Like the very toughest derivations I won't solve. I'll be telling you after solving this expression you will be getting this result. So I won't solve those derivations, whatever derivations will be required like for toughest derivations. But if you need derivations, just ask me in the benzene batch WhatsApp group. I'll be sending you all the derivations, but I won't solve derivations because that's just wastage of time, and that is not required. Okay, you just need to understand how quantum theory evolved, how quantum theory came, why quantum theory came, that you need to understand, and a lot of mathematical tools, those will be required. Fine. So once again, good morning. So tell me, should I start now or I should wait for some time? Should I start or I should wait for some time? Okay, fine. Just one minute, I'm sorry. Okay, fine. So once again, good morning to all of you. So in this class, we will be talking about this quantum theory, or especially if I talk about, we will be talking about quantum mechanics. Okay, quantum mechanics. So before I go into the quantum mechanics, let me tell you two important things, that there are two kinds of mechanics in physics. In physics, two kinds of mechanics, and in chemistry, that means in physical chemistry, we generally deal with the same. One is called classical mechanics. Classical mechanics. Another is called quantum mechanics. Quantum mechanics. So the concept of quantum mechanics was started from year 1900. Okay, the concept was like introduced for the first time in year 1900, and before that we had only classical mechanics. Okay, so what is classical mechanics and what is quantum mechanics? What is the basic difference between classical and quantum mechanics? That you need to understand. So classical mechanics basically says that whatever we see, whatever we feel, everything has, everything has some continuous property, or everything shows continuity. What does that mean? Continuity. But quantum mechanics basically says no, it's wrong. Nothing like quantum particles or quantum objects don't show continuity, they show actually discontinuity. They show discontinuity or discontinuous properties. So you would ask me, what is continuous property, or what is continuity, what is discontinuity? Okay, so let me give you basic examples, then we'll be doing further study, and like automatically you will be understanding what do you mean continuous nature, what do you mean by discontinuous nature. That is the basic fundamental things about classical mechanics and quantum mechanics. Now suppose you are on the roof of your house or of your home. This is the roof of your home. Okay, this is your home. Okay, and you are here. Okay, there are some trees. Okay, here there are some trees, and the mangoes are there, so you want to eat some mangoes, so you are here on your roof. Now how can you like get down from your roof? So you can use this kind of steps. You can definitely use these kinds of steps. Steps are what? Like here, 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 here. So you will be keeping your leg from first time. Suppose this is you, okay, this is you. So you will be keeping your leg first here, then here, then here, then here, then here, then here, and then you will be getting down from the roof. Fine. Now question arises that what does that mean, or is there any other method through which I can get down from my roof? Yes, there is another method. So I hope you have at least seen the swimming pool, and in that swimming pool there are these kinds of situations you may have seen already. Like, let me draw it. These kinds of sliding situations. So I am giving you real life examples because these examples will help you a lot to understand this phenomenon, this continuity and discontinuity. So first of all, do you know this is what? Like in swimming pool, somebody like sits on a body, somebody sits on a sliding plane and they just go like that. And so you are sitting over here and you are automatically coming in that way, and you can easily get down from the roof. There are two methods. One method is you can use steps. Another method is you can use these kinds of sliding mechanics, sliding like machine like that. You are sitting over here, you are automatically getting down over here. So if I tell you basically this is your classical mechanics and this is your quantum mechanics. So in case of quantum mechanics, what happens? Nothing is continuous. So you can keep your leg over here, leg over here, leg over here, leg over here. Wherever you want, you can, like, your whole body is getting slided from this in this way. That means you are touching every section of this sliding system. But if you are talking about steps, you are keeping your leg here, 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 here and here. You cannot keep your leg in between these two steps because there is nothing. Even in between these two steps, because there is nothing. Here you cannot put your leg because there is nothing. Similarly, here you cannot put your leg. Either you have to keep your leg over here or here to get down. That means everywhere you won't get everything. Here you are getting something, then after some gap you are getting something. In between these two, nothing, like there is nothing. That is about discontinuity. So you won't find everything continuously. Here in case of classical mechanics you are getting everything continuously, but in case of quantum mechanics you won't get everything continuously. Here you have something, then you have nothing, then you have something, again nothing, again something, again nothing, again something, again nothing, again something, again nothing, again something. That's why it is called discontinuous. And discontinuity is the property of quantum mechanics and continuity is the property of classical mechanics. That's the basic difference. Okay? So now I hope some of you have a little bit idea, but nothing, like, it's not 100% clear, I know this. So automatically whenever I will be teaching you further, automatically you will be understanding what is quantum mechanics and what is classical mechanics. You will be understanding this. So now let me move to the question that why we need quantum mechanics. Why? Because we had classical mechanics already. Then why we need quantum mechanics, and what happened that at 1900 quantum mechanics has evolved, or we needed another theory. I will be telling you this thing by starting like from 1675 year. So in the year of 1675, Newton, scientist Isaac Newton, for the first time included or incorporated a theory of light that was called Newton's corpuscular theory of light. Corpuscular theory of light. And through this theory of light, he explained a lot of phenomena. So he told that it is the theory of light. So according to this theory of light, whatever light you can see lights, okay, everywhere light is present. Because of light you can see everything. You can see me at your mobile screen because from the mobile screen lights are coming to your eyes. That's why you can see me, right? So definitely everybody, everywhere light is present. So Newton said in his corpuscular theory of light that light is actually the stream of some small particles. and those particles generally travel linearly. Okay, that is the basic corpuscular theory of light. Now you'd ask me, if these are this is corpuscular theory of light, and those corpuscles, so these particles are called corpuscles. Let me write it. These are called, every particle is called corpuscles. So these corpuscles travel generally linearly, in a linear fashion, and whenever they are traveling, they will be giving you different colors. That was the first theory. Now you can ask me, okay, how can I get different colors, because all these corpuscles are like just a particle. So how would I get different color for light? Because light can be yellow light, light can be red light, blue light, green light, violet light, everything. So Newton said that the color of the light depends upon the size of the corpuscles. Size means this is bigger corpuscle, that would show different color. This is small corpuscle, it will show different color, it will show different color, it will show different color, it will show different color. So size of the corpuscles will show different color, and that theory was very good theory according to that time. Okay, that theory was very important theory. Now the problem was with that this theory at that time in 1675, that theory was accepted, because at that time no scientific advancement was there. But after 100 years, like till 100 years this theory was correct, but after 100 years, like some other phenomena got discovered. Those phenomena are called like polarization of light, then diffraction of light, then interference of light. So after 100 years these phenomena was observed, but the problem was, then scientists tried what? Scientists had this theory, Newton's corpuscular theory of light, and they tried to explain these phenomena by this corpuscular theory of light. But whenever they tried, they couldn't explain. That means this theory has some issue. In this corpuscular theory of light, we have some, there are some mistakes, and because of those mistakes I cannot explain this polarization, diffraction or interference of light, these phenomena. So to explain these phenomena, now we need to explain this phenomena, right? So to explain these phenomena, in the 19th century, another scientist came, and he incorporated another theory, and the name of the theory was Huygens and wave theory. Huygens wave theory. Okay. And what about this Huygens wave theory? Huygens was the scientist's name, and he developed the wave theory. And according to this wave theory, he explained all these things, all these polarization, diffraction, interference. He explained accurately. He explained this. Okay. In the 19th century, Huygens explained all the phenomena that was present, that Newton's corpuscular theory of light couldn't explain. Huygens explained everything. Then another scientist came, his name was Maxwell. He further extended the Huygens wave theory, and he told that this light is nothing but the electromagnetic radiation. So light is a wave. Wave means what? Wave theory means light is behaving like this wave. And Maxwell also said that Huygens was right, and I am now extending this wave theory, and he is saying that this light is nothing but the electromagnetic radiation. Electromagnetic radiation. Okay. Electromagnetic radiation. And these electromagnetic radiation has two components. One is called electrical component, another is called magnetic component. And these two components generally stays perpendicularly, I mean with 90-degree angle. So now if I draw in this way, then this is suppose one component, another component should be present in this way according to Maxwell. So it is your electrical field component or electrical component EC, it is your magnetic component MC, and the angle between these two components will be 90 degree, and that Maxwell like extend from the Huygens wave theory, and it was 100% correct. It was also correct. Okay, and Maxwell was the very famous scientist. Okay, very famous scientist. Then everything was going fine. This theory was quite successful. I could explain all these phenomena that Newton's law couldn't explain. Then some other experiments were done. Like scientific advancements will keep on happening, right? So some other experiments has been done, and the name of those experiments were like black body. I am giving you name one by one. First name was black body radiation. Black body radiation. This was one experiment. Okay. Second was photoelectric effect. Second was photoelectric effect. And third was like spectral lines of atom. Spectral lines of atoms. And also other experiments. I am not taking those names. A lot of experiments are done. And then scientists tried to explain all these phenomena. Like these are experiments. These are what? These are experiments. Okay, experiments. Remember, these are experiments. And to verify, to validate those experiments, definitely we need some theory. And then scientists, whatever theory we had at that time, scientists tried to apply those theory like Huygens wave theory, Maxwell's electromagnetic radiation theory, and then tried to explain the black body radiation, photoelectric effect, spectral lines of atoms. But the problem was they couldn't explain with this theory. Okay, from this theory they couldn't explain this phenomena, this one or this one. That means these was experimental results, and experimental results cannot be wrong. That means definitely we had something wrong in this. We had some limitation or something wrong in this Huygens wave theory or Maxwell's electromagnetic radiation theory. Something wrong or some limitation, I can say. And that limitation for the first time solved or like understood one scientist in the year 1900. His name was Max Planck. For the first time he understood that problem, that okay, we can't explain these phenomena, these experimental phenomena with the available theories in the market. We can't explain this. And for the first time Max Planck, actually if I tell you about Max Planck generally a scientist, a theoretical physicist, he was working on thermodynamics. Like, okay, so he was working on thermodynamics. Okay. And he said, okay, as these theories are getting failed, so I will be doing what? I will be incorporating a new theory, and based upon this new theory or based upon that new concept, I will be trying to explain this black body radiation. So Max Planck for the first time tried to explain this black body radiation with his new theory. Okay, with his new theory, and that was the first incorporation of quantum theory or application of quantum theory. And he considered in this case that in case of classical mechanics, I told you everything is continuous, but in case of quantum mechanics or quantum theory, everything would have some discontinuity. So he thought, okay, as by considering the continuous nature of the system, I can't explain this theory theoretically. Now I will be doing what? I will be considering that nothing is continuous, everything is discontinuous. In the case of like those light or other things, everything is discontinuous. And by considering this discontinuity, this Max Planck explained black body radiation, and I will be showing you that this black body radiation is the explanation for the black body radiation using quantum theory was 100% successful. I will be showing you, nothing to worry, I will be showing you. Okay. So now let's talk about this black body radiation first. What is black body radiation? Then I will be showing you how Max Planck solved the theoretical problem with black body radiation, that these theories was unable to explain the black body radiation, but Max Planck's theory is able to explain the black body radiation. Understood? Now let's understand this. So to understand this black body radiation by Max Planck, we need to understand what is black body or what is black body radiation. So first of all guys, how many of you, can you write in the comment box, how many of you know what is black hole? What is black hole? How many of you? Just comment first, how many of you already know what is black hole? Then if you know this, it will be very easier to understand what is black body. Let's see. I know you are from chemistry or not from physics, but maybe some of you has little bit interest. So can you try? What is black hole? How many of you know already? Because it's, if you understand black hole, then if you don't know, please say no, I don't know. Nothing to worry, I'll be telling you. But please do respond. Don't be lazy. Anybody? Nobody? Okay, if you don't know, say no. Don't stay silent, please. This is the okay, no. Fine. That means you don't love space. Okay. Fine, great. So to understand black body, what happens? We need to understand black hole. So black hole is a giant object present in space. Okay. And what happens? Why it is called black hole? So it is called hole. That means like hole is what? Where everything like goes into, but nothing can come out. That is all. It is called hole. So why it is called black hole? So you know that Earth, you know Sun, you know other stars, you know everything, and all these Sun, Earth, everybody has some gravity, and as Sun has like heavier gravity, more gravity than the Earth, that's why Earth is revolving around the Sun. So black hole is an object on the space, and that has a very heavy mass, and as it has very heavy mass, a lot of mass it has a very high gravitational power. And you know, suppose Earth has gravitational power, that's why we are here on the Earth. We cannot go, like by jumping we cannot leave the Earth. But if you go to the moon has less gravitational power. That means moon attracts the objects less than the Earth. Similarly, if I talk about this black hole has the highest gravitational power in comparing to the other systems present in the universe. In the universe, black hole are the systems, black holes are the objects, those has highest gravitational powers, and from these gravitational power, what they will do, they will attract everything towards itself, everything. So it can it can attract you, it can attract other stars, it can attract any planet, it can attract light, it can attract sound, it can attract time, it can attract anything, everything. So that's why we say whenever in the black hole its gravity is too powerful that even light cannot escape from this black hole's gravitational power. That means suppose here you have black hole and you are showing any light, so its gravity is too powerful that if you shine light over here, light also getting attracted by the black hole. So light cannot escape from the black hole. Even light cannot escape from the black hole. Understood? This gravity is too powerful. Even not only light, even time cannot escape from the black hole. At black hole, time equals to 0. At black hole, time equals to 0. Sound cannot escape from the black hole. If you are applying some sound waves will be attracted towards the black hole. This is all about black hole. And same thing we'll be doing for this black body, but black body doesn't have that amount of gravitational power. And now, if I tell you why it is called black hole, now suppose lights are coming, or so now suppose I am giving you an example. Okay, suppose look at this thing. So why you can see this thing? Why I can see this thing? Because light is coming, reflecting on this thing and coming to my eyes. That's why I am seeing this thing, right? That is the logic. But what happens in case of black hole? Black hole has a lot of gravitational power, and because of that, whatever lights are going towards the black hole, they never come back. They generally goes, and black hole is attracting them. And if light cannot come back, so how would it look like? It will be looking like black, because light cannot come back. So if from here light cannot come back, so what I will be saying? It will be black. In absence of light means what? Black. That's why as light cannot come back from here, that's why it is called black hole. It is looking like a black. Understood? So the same thing I will be applying for this black body. So black body like doesn't have all these properties. Black body means it's a body. Suppose I am drawing a body. This is the body. This is the body, and in this body, if I am incorporating some light, suppose some light or some radiation, because Maxwell already told light is nothing but light is nothing but the electromagnetic radiation. So I am applying some light or some electromagnetic radiation. Okay. So if I am incorporating light in this black body is just a body, nothing else. What happens? Black body absorbs all the light. It absorbs all the light. So as it absorbs all the light, that means light cannot go back by reflection. It absorbs all the light. So as light cannot go back by the reflection, so can we see any color that is coming out from the black body? No. So if light is not getting reflected, how can I see that object? How can I understand that? How can I see that what light is coming out? Light is every light, every wavelength light is getting absorbed. Nothing is getting out from the system. Whatever light you are shining, that is getting absorbed by the black body. So if everything is getting absorbed, so it will not release anything. That's why it is called black body. So please, if you understood this black body's property, write in the comment box, write C, clear. Write C in the comment box if you understood what is black body. Black body absorbs all the light, and that's why it is not reflecting any light. That's why it is looking like black. So it is the property of black body. Okay. Now, what is black body radiation? What is black body radiation? Now, suppose what happened initially, I incorporated a lot of electromagnetic radiation or a lot of light, and those light was getting absorbed by the black body. Now I am doing one thing, I am adding some heat to the black body. So whenever I will be adding some heat to the black body, what will happen? Temperature of the black body increases, right? And whenever temperature of the black body increases, what happens? This black body now starts emitting light, whatever it absorbed. So initially it was absorbing only light, it was not releasing any light, it was not reflecting any light. That's why no light was coming from the black body. That if no light is coming from the black body, no light is getting reflected from the black body, so it will be looking like black. That is all about black body. And now if what happens, if we add heat, temperature of the black body increases. So now whatever light it absorbed, all those lights will be coming out in the form of radiation. In the form of what? Radiation. In the form of radiation. And that radiation is called black body radiation. So if you understood this phenomena, what is black body and what is black body radiation, write C in the comment box. Please write C. Don't be lazy. You are very lazy, guys. Don't be lazy. Just you have to write or see and send. Just do it. I need to make sure that you understood everything. Otherwise, you will be sitting like normally and saying, okay, oh, let it go. I don't need to understand it. But you have to understand it, okay? So that's about black body. That's about black body radiation. Now, before I move forward, I need confirmation from you. What is that? Did you understood or not? Then I am moving forward. That's the logic of live classes, okay? Otherwise, what do you mean by live classes? If you just want to look at the screen, then that is good in recorded classes as well. That you can do as in recorded classes as well. So what is the meaning of live classes? So yes, I need confirmation from you, then I'll be moving forward. That did you understand what is black body and what is black body radiation? Anybody? I can see like students are watching, but they are not interested to comment. Why is that? If you don't understand, say that here I am having problem. But why you are not commenting? Seriously? Okay, then I won't ask ever that whether you are understanding or not. I'll be keep on teaching you and you will be keep on noting down everything. Because my teaching style is different. I need like after 10 minutes or 15 minutes, I need one C in the comment box from you that you are understanding everything. Okay, you are telling me say again. Okay, stream is little bit like stream is to delay. Is that true? Say again means what? Say again. Please ask your question properly. So if I am asking you, then you are asking that say again. If I don't ask you, you will be ignoring it. That's not good, yeah, that's not good. You have to say that I need to understand this once again. You have to say from your side. If I don't ask you that is that clear or not, you won't say anything. Please don't do these things, okay? If you are not understanding this, tell this. These are not too simple things. Nobody will teach these things, okay? If you want to love quantum mechanics, you have to understand these things. And you are like a lazy student, you are just sitting. Don't do this, please, okay? Don't do this. Don't be lazy. You just need to say one C. And in that case, you are doing like but please don't do that, because like whenever I am teaching you, like simply I will be expecting that you should cooperate at least. You should say that okay, you are understanding or not. That's what I am asking, nothing else. So I am repeating once again, then I am moving forward. I want to never ask you that whether you are understanding or not. Fine. So what is black body and what is radiation? Black body is basically a body, an object. This is my object I am drawing in this way, okay? So black body will be an object that absorbs all the light. And if it absorbs all the light, what happens? Suppose I am absorbing all the lights. So why you can see me? Have you ever thought why you can see this object? Because light is coming and getting reflected from that object and come back to your eyes. That is the logic of black body. That is the logic of like you can see any object. Now what is black body? Black body means a body that doesn't reflect any light. It absorbs all the light. So if it absorbs all the light, no light will be getting reflected from that black body? Definitely yes. That means you can't see, you will be seeing that object as black. Because if light is not coming out, would you see any color? No. That's why it is called black body. It absorbs all the light. Whatever light you are incorporating, whatever light you are shining, all the lights will be absorbed by the black body. And what about this radiation? Radiation is nothing but whenever you are adding heat to the black body after absorbing all those lights, what will happen? You are adding heat now. So whenever you are adding heat, the energy of the black body is increasing, and then it will be doing what? It will be now releasing light, releasing radiation, or releasing light in the form of radiation. Whenever you are incorporating heat or whenever you are increasing the temperature of the black body. That is why it is called radiation. Initially it was black body, that is it was not emitting any light. Now you are adding heat, temperature increases, then again that it is whenever temperature increases, it is releasing some radiation. That's all about black body radiation. Now whenever this was one experiment, this black body radiation was what? One experiment. And from this experiment, scientists got some results. What kind of results? So they measured that whenever they are incorporating this heat, the black body is releasing some light or some radiation, and they measured the wavelength of the radiation, because radiation is nothing but electromagnetic radiation, electromagnetic wave. So electromagnetic wave means what? It is electromagnetic wave, and this will be what? This will be what? This will be what? One wavelength. This will be what? Another wavelength. So every electromagnetic radiation has corresponding wavelength. So scientists measured the wavelength of the emitting radiation that is coming out from the black body after applying heat or after increasing the temperature. And also they not only measured the wavelength, they also measured the frequency of the radiation that is coming out by applying the heat. Okay, frequency of the radiation. So also wavelength, lambda, and also the frequency they measured experimentally. Okay, and whenever they experimentally measured all those things, they got two different kinds of plot. So one they plotted like lambda versus intensity, or sometimes they are called energy, and another frequency versus like this intensity or energy. They plotted two different plot from the experimental result. Okay, they plotted this intensity versus wavelength, intensity versus frequency. They plotted these two, and they got like very important plots. And what is this plot? Whatever radiation is coming out after applying heat, that radiation's intensity versus that radiation's energy, that radiation's intensity versus that radiation's wavelength, and not only that, that radiation's intensity versus that radiation's frequency. They plotted these two plots, and they got some important plots, important experimental plots, and the plot was looking like this. The plot was looking like this. Okay, so it was like this plot. Okay, these are not three different plots. This plot was at temperature T1, this plot was at temperature T2, this plot was at temperature T3, and temperature T1, T2, T3, they are increasing temperature. Okay, that means they were incorporating some heat, and the temperature of the black body was T1, and they got this plot, intensity versus wavelength, this plot. They increased temperature a little bit, they got this plot, and then they increased temperature little more bit, then they got this plot. These three plots they are getting, and also if you increase the temperature, it will be like you will be getting T4, T3, T5, T6, a lot of plots will be there. This was your intensity or energy versus wavelength. Okay, now you know the relation, guys, already, that frequency is equals to nothing but c by lambda, nu equals to c by lambda, and c is a constant, speed of light in vacuum, that's a constant, right? So I can write from here that nu is proportional to 1 by lambda. That means whatever I will be getting, like if wavelength increases, frequency decreases, or vice versa, these are inversely proportional. And similarly, based upon that, we can understand the plot, how it will be looking like whenever we will be drawing intensity or energy versus frequency. So whenever you are drawing this plot, you will be getting this kind of thing. this kind of thing. Okay, it is at T1, T2. I hope you have seen this, T1, T2 and T3, and the increasing temperature in this way. And similarly in case of T4 you will be getting this. So now you can notice that here this plot is looking like this plot is getting shifted little bit left and left. So at T1 the maximum height was there, and that belongs to this wavelength, this lambda. This x-axis represents lambda, so this lambda. At T2 this was your height. At T3 this was your height. Okay, look at this. That means whenever you are increasing your temperature, the maximum intensity, this is called maximum intensity. The intensity definitely increases. Definitely intensity or energy. You are increasing temperature, energy will be increasing. It's correct. It is increasing. But the maximum intensity or maximum energy at the wavelength is decreasing. So at T1 temperature, wavelength was at this wavelength, you are getting maximum wavelength, maximum intensity. At T2 temperature, at the less wavelength, look at this, less wavelength decreasing, you are getting maximum intensity. At T3 temperature, furthermost at less wavelength, you are getting this in maximum intensity. That means your maximum intensity is increasing with increase of temperature, but you are getting your maximum intensity at less wavelength whenever you are increasing your temperature. But as you know that wavelength and frequency, they are opposite inversely proportional. So opposite thing will be seen for in case of frequency. This one and this one. So what is happening? At lower temperature, frequency was this. At this frequency you got maximum intensity. You are increasing your temperature. At higher frequency you are getting more intensity, and further at higher temperature, at more higher frequency you are getting your maximum intensity, I mean maximum height. So in this case what is happening, your maximum height you are getting in this way, they are varying in this way, and this is the result that they got experimentally from the black body radiation. Now we need to understand these experimental things from theoretical models, but in the market at that time, in the market there was no theoretical model present. There was no theoretical model, because whenever they tried to explain these two plots by the available classical mechanical theory, those classical mechanical theory couldn't explain all these theories. Those classical mechanical theory couldn't explain all those theories. Okay. So let me tell you the name of those classical mechanical theory which tried to explain this plot. Okay. So first classical mechanical theory was Stefan Boltzmann law. Then Wien's law. Then Rayleigh-Jean's law. These three laws came to explain the classical mechanical, to explain the black body radiation. But all these laws were classical mechanical laws, or all these laws follow classical mechanics. That means they will be showing some continuous nature, continuity, right? And these laws tried to explain these three laws tried to explain the whole black body radiation curve. So the black body radiation curve is looking like this. I am drawing only at one temperature. This is the black body radiation curve. It is looking like this. But the problem with this classical mechanical theory was that these three laws could not explain, or these three laws perfectly explains the black body radiation. But remember one thing, if I want to draw a particular plot, definitely I should draw that particular plot from one single theory or law. But what happened? This theory was explaining a little bit part, This classical mechanical theory was explaining a little bit part. This theory was explaining a little bit part. And if you add all these three theories, then by like the collection of these three theory can explain the full plot, full graph. Full graph means what? Full black body radiation phenomena. So this black body radiation is giving you this plot at a particular temperature. I am taking only one temperature. So these three classical mechanical laws are required to explain the total plot. That means I can write one single line that no single theory can explain the total BBR means black body radiation. So no single theory can explain. So to explain that, quantum mechanics generally comes. Okay, to explain the full plot by a single theory, quantum mechanics is coming. And now if I tell you, what about this Stephen-Boltzmann law, what about this Wien's law, what about this Rayleigh's law? Because I told you these three laws explains a little bit part of the plot, a little bit the part of the black body radiation. So this Stephen-Boltzmann law generally, this law generally calculates the total energy. Let me tell you, this calculates the total energy. Okay, so this law is done. Total energy of the radiation that is emitting, that is getting out from the black body, that the radiation's energy, this has been measured, this has been calculated by the Stephen-Boltzmann law. So Stephen-Boltzmann law only does this thing, total energy it calculates. Then what really Wien's law says? Wien's law basically explains the black body radiation curve at the lower wavelength region. Lower lambda region. Okay, and this Rayleigh's law explains the black body radiation at higher wavelength region. These three laws. Okay, so what do you mean by that? That means these law cannot explain the full curve of the black body radiation. These law cannot explain the full curve. These law cannot explain the full curve. But if you add these three laws, if you collectively understood these three laws and apply all these three laws, then these three laws can explain the full property, total property. But it is not an acceptable theory. These are three different theories. That's why I have written this line, that no single theory can explain the total black body radiation. That's why I have written this line. What does that mean? It means that Wien's law is explaining this part of the plot, Rayleigh's law is explaining this part of the plot, and the Stephen-Boltzmann law explains the total energy of the plot. But these one cannot explain the full plot, these one cannot explain the full plot, these one cannot explain the full plot. That means I can write this line. That means no single theory can explain the full plot that you are getting experimentally. That means in case of classical mechanics we have some limitation, or classical mechanics we had or have some limitation. That's why any single theory cannot explain the full plot of the black body radiation. Then another scientist came, his name was Max Planck, I told you, and he explained this full plot by one single theory. And he told, okay, now listen, I can explain this full plot by only one theory. I don't need three different theories to explain. That means my theory was right, my concept was right. That means quantum mechanics is right. That's the method that I will be showing you, that how Max Planck showed that only from one theory I can explain the full black body radiation curve. I don't need three different theories. Okay. And these three different theories was classical mechanical theories. So this theory was explaining at the lower wavelength region. Lower wavelength means lambda increasing. Lower wavelength, lower lambda. Higher wavelength, higher lambda. So this law was explaining at higher wavelength region. That means if you draw a plot from Wien's law, you will be getting this kind of plot. I will be showing you this thing as well. Now before I go to the Max Planck's law, let's see what Stefan Boltzmann law says, what Wien's law says, and what Rayleigh-Jean's law says. Let me show you one by one. So first of all, Stefan Boltzmann law. So in 1879, for the first time, Stefan did the black body radiation experiment to develop a theory. Okay, so BBR experiment EXP, and in 1884, after 5 years, this scientist Boltzmann made the theory. Okay, made the theory. So Stefan did the experiment, Boltzmann did the theory, made the theory, and from this theory they calculated total energy of the black body radiation. Total energy of the black body radiation means how much energy the black body is releasing whenever we are applying heat in the form of radiation. How much energy it is releasing, that is called total energy. So this total energy I am representing with E. It is actually E proportional to T to the power 4. That means with the increment of temperature, energy energy will be increases. So if you increase more temperature, more energy will be releasing. That's the logic. That's why it is proportional, and it is proportional in this way. And now if you want to take a constant, you can take this E equals to, I am taking the constant sigma T to the power 4. Okay, and this equation is if I want to make this equation more accurate, then it will become C by 4 E equals to sigma T to the power 4. That is more accurate equation. So in some book you will be getting this expression, in some books you will be getting these expressions. Both these expressions are correct. Okay, but both these expressions are correct, but this is more accurate one, that's all. So C means what? C means, you know, C is velocity of light in vacuum. That's about C. Okay, so now what do you mean by this sigma? So this sigma is called Stefan constant, and the value of the sigma is actually this 5.67 multiplied by 10 to the power minus 8 joule meter to the power minus 2 second inverse and Kelvin to the power minus 4. This is the value of Stefan constant in SI unit, and if I change it, if I want to get the value in CGS unit, it will become what? 5.67 multiplied by 10 to the power minus 5, then arc centimeter to the power minus 2 second inverse Kelvin to the power minus 4. This will be the value of this Stefan constant in CGS and SI unit. Okay, great. And through this Stefan Boltzmann law, we can calculate the total energy of the electromagnetic radiation that is coming out from the black body. That was the Stefan Boltzmann law, classical mechanical law, and through that we can calculate total energy. Now what Wien's law said, let's calculate. Let's see Wien's law. So Wien's law is basically this one. Wien's law means, actually it is not Wien's law, actually it is Wien's displacement law. If I write it, Wien's displacement law. So Wien's displacement law says, Wien's displacement law gives this equation: E lambda d lambda equals to A lambda to the power minus 5 e to the power minus b by lambda t d lambda. And I am not deriving all these expressions because these are classical mechanical expressions, so you don't need to derive this. Just keep patience and understand, then it will be very, very interesting. Trust me, it will be very, very interesting whenever I will be showing you Maxwell's theory of electromagnetic radiation or quantum theory. It will be very, very interesting. So Wien's displacement law was this, And from this Wien's displacement law, if we apply that maximum wavelength, if we apply the concept of maximum wavelength, then we will be getting this expression. That is called Wien's law. So Wien's displacement law is the mother law, and from this law I am getting Wien's law. And that Wien's law says that at maximum lambda or lambda max will be inversely proportional to temperature. This Wien's law said. And from here, if I make it lambda max multiplied by T, there will be a constant. And that constant has some value 2.8 into 10 to the power minus 3 meter Kelvin. That's all about the lambda max. That's all about the lambda max. Okay, lambda max T equals to this. This is about Wien's law, this is about Wien's displacement law. Fine. And these Wien's law, if you plot this Wien's law like in this way, like lambda versus intensity or energy or intensity, so you will be getting these kinds of law. So this kind of thing. But the black body radiation law is how? It is looking like, look at this, it is looking like this, but I am getting these kinds of law. It means what? This Wien's law is only explaining the black body radiation plot from the lower wavelength region, this part. It cannot explain this part. Understood or not? That this law is explaining only this part. This law is explaining only this part. Only this part, okay? It is not explaining this part. That's why the plot is looking like this. If you draw this one from this plot, that means this Wien's law is applicable at lower lambda region. Okay. Now let's come back to the next one. Number 3. Number 3 law was classical mechanical law was Rayleigh-Jeans law. It was here your Rayleigh-Jeans law, and this Rayleigh-Jeans law was like that. So from the Rayleigh-Jeans law, Rayleigh-Jeans was two scientists, and they did calculate some values. What are the values? That they thought that this electromagnetic radiation which are coming out whenever we are increasing the temperature of the black body, and these electromagnetic radiations are behaving like vibrational oscillators, or simply oscillators. These electromagnetic radiations behaving like oscillators, and whenever electromagnetic radiations are coming out, that means according to them some oscillators are coming out. And what they did, they calculated the number of oscillators. Okay, so number of mode of vibration per unit volume in the wavelength range lambda to lambda plus d lambda equals to dn. Okay, so they just did one thing. They calculated the number of mode of vibration per unit volume. Means what is the number of mode of vibrational oscillators those are coming out? How many number of mode of vibrational oscillators those are coming out from the black body? That they calculated. Okay, and why I am saying you that it is lambda to lambda plus d lambda. Suppose this is the range, this is 0, this is lambda, this difference is called d lambda. So what is the distance? Lambda plus d lambda. So they are talking about in these range, lambda to lambda plus d lambda. So in these range, how many oscillators are present? How many number of mode of vibrations are present? Those are coming out. So they calculated this value. Okay, and they got one expression for that. So dn, they got dn equals to 8 pi by lambda to the power 4 d lambda. They got this value, that how many oscillators, how many mode of vibrations are coming out, that is dn, and that is actually 8 pi by lambda to the power 4 d lambda. Okay, they calculated this value. Okay, and after that, from equipartition and also from classical mechanics, from CM, equipartition principle of energy, EPPE. I can write equipartition principle of energy. EPOE, equipartition principle of energy. Like one vibrational mood has energy equals to kT. Okay, so you can ask me how I am getting this kT. This thing I will be teaching you in gaseous state chapter. Gaseous state, okay? Or you can check my YouTube channel. I have already uploaded the video on gaseous state. So you can, this thing you will be getting from gaseous state. That from equipartition principle, which is equipartition principle, that I will be teaching you in gaseous state. So from equipartition principle of energy, one vibrational mood has energy kT. One vibrational mood, okay, will have energy kT. So I know that total number of mode of vibration is this. One mood has energy kT. So there, what will be the total amount of energy? KT multiplied by this. So total energy again equals to what? From Rayleigh's law, total energy E lambda d lambda equals to dN is the number of mode of vibration and kT is the energy for one mode of vibration. So for one mode kT, for this mode kT into this, and that in this case if you put the value of dN, dN is what? 8 pi by lambda to the power 4 d lambda, 8 pi by lambda to the power 4, then kT I am writing, then I am writing d lambda. So that is the expression that we are getting from Rayleigh's law. Now if I draw a plot for Rayleigh's law, here it is lambda, here it is intensity or energy. I will be getting this kind of plot. And if you look at why I am getting this kind of plot, is this plot is not black body radiation plot. This plot is looking like this. If you look at this black body radiation plot, I am getting this kind of plot. That means this Rayleigh's law only satisfied this region of the black body radiation curve. This part, this law is not satisfying. And this region means what? Higher wavelength region. Come back. That means this Rayleigh's law is applicable only at higher wavelength region. Understood this one? If you understood this one, write U in the comment box. This explains at higher wavelength region. So we got three different formulas from classical mechanics. One is Stephen-Boltzmann law that calculates total energy. Second is Wien's law that calculates that gives this expression and this expression, and it is satisfying the black body radiation curve at lower wavelength region by giving this kind of plot. And in case of Rayleigh's law, we get this kind of plot, and that is satisfying the black body radiation experimental curve at higher wavelength region. Okay, in this way they are satisfying. Now the logic is that only one theory cannot explain the full curve. If I tell you that Wien's law is satisfying in this region, Rayleigh's law is satisfying in this region, Rayleigh's law, let me write it, RJ law is satisfying in this region. That means if I consider this region, that is Wien's law and RJ law, if I consider both of these law, I will be getting the full curve. But there are two different theories that we need to explain the full curve. But that thing won't work. I need only one single theory. So to do this job, what happened? Max Planck came. Okay, and he for the first time he considered quantum mechanics or quantum mechanical theory, and in that theory he told that there is some discontinuous nature or discontinuity property of the system according to Max Planck. And discontinuity means what? I already told you, there are some specific energy levels you will be getting. You cannot get this energy level or this energy level. Either you will be getting energy level over here, or you will be getting energy level over here. You cannot get energy over here, or over here, here. There will be some specific energy levels, and if I show you this energy is increasing in this way, So either you will be getting this energy or you will be getting this energy. You cannot get this energy. No. That is classical quantum mechanical concept. And what about classical mechanics, that is continuous nature? You can have all the possible energy like this. You can get energy over here, you can get energy over here, here. You can get energy anywhere according to classical mechanics. But according to quantum mechanics, you cannot get all the energies. Either you will be getting this energy or this energy, this. That means there will be some specific energy levels according to quantum mechanics. Specific energy levels. Specific E level. Okay. And why it is called discontinuous property? That means here you are having something, here you are not having something. Having something, not having something. Having something, not having something. Specific values you are getting. In between these two, you are nothing. You have nothing. No energy levels are there. That means you have nothing. That means I am not getting my energy continuously. I am getting my energy discontinuously. Discontinuous means here I have energy, then discontinuity, here I have energy, again nothing, here energy, nothing, here energy, nothing, here energy, nothing, again energy. And this will keep on going. That's the property is called discontinuity. And Max Planck did what? Max Planck basically tried to understand this thing, this black body radiation through this discontinuous property. Okay, through this discontinuous property. Max Planck trying to understand that. How? So he thought that the energy that those are coming out from the black body, this energy, those are coming out from the black body, those energies are coming out in the form of oscillators. Oscillator means those has oscillation. So you know what is oscillation in class 10 plus 2 physics. Energy generally comes from the system through oscillation. Oscillation means like vibration, you can think of. Vibration. So oscillation means some oscillators are there. Oscillators. Some oscillators generally oscillates. That means energy is coming out, radiation is coming out by the application of heat in the form of oscillators. And those oscillators are having some specific amount of energy. And their energy generally depends upon, frequency of those oscillators. Understood properly? Frequency of that oscillators. Max Planck told that. And as we are taking this proportional, that means we have to take the constant, then he took E equals to one constant, another nu. What was that constant? That constant was AH. And I hope you know this expression. And this expression came from this logic. That energy is proportional to oscillation, like energy is proportional to frequency, and like which frequencies radiation is coming out from the black body. That was the frequency. And the energy was the corresponding energy. And to make this equal, he took one constant that is called Planck's constant. That is called Planck's constant. Okay. And then he calculated the value of Planck's constant H. That will be what? H will be equals to E by nu. I can write. And he calculated this value E by nu for the oscillator, that was about 6.626 into 10 to the power minus 34. What will be the unit? I don't know the unit for the time. Or in 6.626 into 10 to the power minus 27. What will be the unit? I don't know the unit. It is very simple. So you know what is the unit of energy? You know unit of energy is actually joule in SI, arc in CGS. Just put arc, joule. Great. What is the unit of frequency? Second inverse. So divided by second inverse means what? Here I will be getting second. So in this way you are getting joule second unit or arc second unit and the value of Planck's constant. And in this way Planck's constant generally came. So he thought that one oscillator or lowest energy of the oscillator, I can say lowest energy of an oscillator, that will be equals to epsilon or h nu. Okay. Now suppose there are some other oscillators which has more energy than these oscillators. It may be present that some oscillators, those are coming out, the radiations which are coming out, those will be behaving like oscillators. So some oscillators may have energy greater than this value. Now he didn't say that any value is possible. He told that if you have any higher energetic oscillator, that will be represented in this way: n epsilon or n h nu, and the value of n should be either 1 or 2 or 3 or 4 or 5 or dot dot dot. You cannot have value 1.5 or 2.5 or 3.5. You cannot have. This is the lowest value or lowest energy of the oscillator, E equals to h nu. And if any oscillator has higher value, that value will be integral multiply of the lowest value. Integral multiply means this n would vary in this way. So suppose another oscillator has higher value, that can be 2h nu, or that can be 3h nu, or that can be 4h nu, or 5h nu, or 6h nu, or dot dot dot. But you cannot get these, all these values are correct, all these oscillators energy are correct, but you cannot get values like 2.5h nu, you cannot get, or 4.2h nu, you cannot get. That means you are not getting all the values, you are getting some specific values, either this value or this value, this value, this value, this value. These values, suppose n equals to 1, 2, 3, 4, 5 and 6. You cannot get 1.5 h nu, you cannot get 2.5 h nu, you cannot get 3.5 h nu. You will be getting only some values, specific values, either 1 h nu, or 2 h nu, 3 h nu, 4 h nu. That means we are getting some specific values, not all the values. In case of classical mechanics, we should get all the values. N can be 1.1, 1.2, 1.3, 1.4, 2.5, 2.6, 2, 3, 4, 5.1, 5.6, any value. That's why it was continuous. Everywhere we will be getting value. But in case of quantum mechanics, we won't get values everywhere. That's why it is called discontinuous. Understood quantum mechanics? I mean, with the basic logic of quantum mechanics. So for the first time, Max Planck did calculate this thing in this way, and finally he calculated the total energy of the oscillator. Total energy of the oscillators which are coming out from the black body. Total energy. And he got this expression. E lambda d lambda equals to 8 pi hc equals divided by lambda to the power 5 1 by e to the power hc by lambda kt, then minus 1. This is the expression that Max Planck got, and this expression is the successful expression, quite successful expression. Why is that? This expression can explain the full plot. This expression can not only explain the lower wavelength region, it also explains the higher wavelength region. Now question arises, is it possible to draw a plot like E lambda versus lambda plot from this kind of complicated equation? Is that possible? Because this equation is called like Max Planck blackbody radiation PBR expression, blackbody radiation expression. And if you draw this plot, you will be getting this kind of plot. But yeah, I know that it is, you can do it, but how can I show you? Because here lambda is present, here lambda is present. How can I show that yes, this plot is really like this equation is really giving you this plot? So I will be using some indirect method to show you. I know already that in the lower wavelength region, Wien's law satisfies this plot. In the higher wavelength region, really RJ law satisfies the plot, like over here. Understood properly? What I am telling you, please understood properly. I know in the lower wavelength region, Wien's law satisfies the plot. In the higher wavelength region, Rayleigh's law satisfies the plot. Not only that, if I want to get total energy that has been like satisfied by the Stefan Boltzmann law. Now what I want to do, if I cannot draw this plot from this equation, I know. But now if I show this thing that in the lower wavelength region, if I get Wien's law from this law, again understand, in the lower wavelength region, if I get Wien's law from this Planck's law, then I can say that at lower wavelength region, Max Planck is explaining this Wien's law. That means this part of the plot. Similarly, at higher wavelength region, if I say Max Planck's expression is satisfying the RJ law, or I am getting RJ law from Maxwell's equation, Max Planck's equation, then I will be saying that at higher wavelength region, this Max Planck's law or expression is satisfying the RJ law or satisfying the plot in the higher wavelength region. So I want to draw this plot from this equation. I will be satisfying Wien's law and RJ law. That means I will be satisfying this part and this part. And also I will be satisfying the Stephen-Boltzmann law to calculate the total energy. And if I can satisfy all these three classical mechanical laws from this one expression, that means I can say this one expression is enough to give me the total plot. Because in lower wavelength region, Wien's law is correct. Higher wavelength region, RJ law is correct. Stephen-Boltzmann law is correct to calculate the total energy. But there are three different theories. Now if I get Stephen-Boltzmann law, RJ law and Wien's law from one single theory, then I can say that this single theory can explain the full plot. That is the thing that I am going to do. So now let's derive all those expressions, this one and this one, from this one by one. So first of all, I am starting with the Stephen-Boltzmann law. Number one, Stephen-Boltzmann law. How can I explain this? And I'm sorry guys, electricity is disturbing a lot. Every day this is happening. Just one second. I'll be there, okay? I will be discussing all these things. It will be coming back within 2 minutes. Okay, it came back. Nothing to worry. So, how Stephen-Boltzmann law can be explained from the Max Planck's equation? Let's check that. Because Stephen-Boltzmann law is not at lower or higher wavelength region. It calculates the total energy. How can I do that? So it can be done that how to calculate total energy. It's very simple. Total energy E equals to what? Now look at this plot. If you look at this plot, here x-axis represents lambda and y-axis represents energy or intensity. So at this point lambda is 0 and this plot will be meeting with this x-axis at infinity. So lambda is 0 here, lambda is infinity here, and this plot will be there till infinity, and this area is called total energy. From this plot, this area is called total energy. Okay, so how can I calculate total energy? So I know the expression from the Max Planck's equation. That is the energy expression, and E lambda d lambda is this. I mean, okay, I'm sorry, I have to put a d lambda over here. Please guys, make it correct. I have to put a d lambda over here. Now it's funny. D lambda over here. So I have got the energy expression, and I know lambda varies from 0 to infinity, and this is the total energy. So I can do this thing that from this expression, if I do this kind of integration, that 0 to infinity, what is 0 to infinity? Lambda wavelength. Then E lambda d lambda. That means E lambda d lambda means the full expression. And if I do this, if I now put the value of E lambda d lambda, that means 0 to infinity 8 pi hc divided by lambda to the power 5 1 by e to the power hc by lambda kt minus 1 and d lambda. So if you now solve this integration, I am not going to solve it. I am giving you as your homework. If you are interested, you can solve it, but I am not going to solve it. If you solve this integration from 0 to infinity, 0 to infinity means from this region to this region, if you solve the full integration, you will be getting this total value. That is the significance of integration, and that value is actually total energy. And if you do this, if you solve this integration, let me write what you will be getting. You will be getting 8 pi to the power 5 k to the power 4 divided by 15 ac whole cube and t to the power 4. You will be getting this expression. That means I am getting E equals to this, total energy equals to this, and that I have calculated from Maxwell's equation. Max Planck's equation. I mean this equation that I got from quantum mechanics. Okay, this I am getting from quantum mechanics. And if you look at this expression properly, what is this? If I consider this is like pi is constant, k is Boltzmann constant, h is Max Planck's constant, c is velocity of light into vacuum. All these are constants. So can I take one single constant for this sigma? T to the power 4 E equals to, what is this? It is nothing but the Stephen-Boltzmann law. That means from Max Planck's equation I am getting Stephen-Boltzmann law. From quantum mechanical law I am getting classical mechanical law. Yes, I am getting. That means these quantum mechanical Max Planck's BBR expression is satisfying the Stephen-Boltzmann law. Is satisfying the Stephen-Boltzmann law. This one, look at this. Stephen-Boltzmann law is E sigma to the power E equals to sigma into T to the power 4. And what is the value of sigma? Sigma value is this. Now what I want to do, I want to check that whether I am getting, if you put the value of pi, k, h, c, if you put all the values over here, do you know how much value you will be getting? You will be getting same value. You will be getting the same value. If you put all these values, sigma value, this is called sigma. If you put all the values, you will be getting sigma equals to 5.67 multiplied by, I forgot the value, what was that? 5.67 multiplied by 10 to the power minus 8. Okay, I am taking it into SI. 10 to the power minus 8 joule, meter minus 2, second minus 1, Kelvin to the power minus 4. I will be getting this expression. Sigma expression will be this. Okay. And I am giving you this as your homework. Don't be lazy. If you want to love this, you have to do this in your as your homework and submit it in the WhatsApp group, Benzene batch WhatsApp group. Okay, submit it. Like whether by putting pi, k, h and c, you are getting this value. If you are getting this value, then definitely your expression is correct. Okay, that means I am getting my Stephen-Boltzmann law from Max Planck's expression. Similarly, if I want to get the second expression like Wien's law or Wien's displacement law, Wien's law for simplicity, Wien's law, and Wien's law is applicable where? At lower wavelength, at low lambda. So at low lambda means what? This was my Max Planck's expression. Let me write it over here. This is my Max Planck's expression, right? So whenever lambda is low, because this Wien's law is applicable at low lambda value, lower wavelength region. So when lambda is low, what happens? If you look at this section, if you look at this part, e to the power hc by lambda kt, okay, minus 1. If you look at this section, whenever lambda is low means what? Down below side is low, above side will be definitely higher. That means it is higher means overall term will be higher. It is low means what? It is low means this is very simple thing, a simple value like 5 by 1.1. That means above term is fixed. Above term is bigger. So if lambda value is low, this term will be bigger, overall term will be bigger. And if overall term is bigger, then it is too much big than 1. Therefore I can say, therefore e to the power hc divided by lambda kt is very bigger than 1. That means I can say I am taking this, actually this is equal to nothing but e to the power hc by lambda kt. I am neglecting this 1. So because with respect to this 1, this term is too much bigger at lower wavelength region. and because of that I am taking only e to the power hc by lambda kt, this one. I am ignoring this one. Now if I put this value at lower wavelength region, so why I am doing this? Because I know this law is applicable at lower wavelength region. So if I put this value in the place of this, if I put this value in the place of this, what will happen? Let's see. Therefore E lambda d lambda equals to 8 pi hc by lambda to the power 5 into 1 by e to the power hc by lambda kt. That I can write in this way. Therefore E lambda d lambda equals to 8 pi hc by lambda to the power 5 e to the power minus hc by lambda kt. I can write in this way. Okay, I can write in this way. Fine. And now this is my expression. Now this expression I want to write in this way. E lambda d lambda equals to a lambda to the power minus 5, because it is lambda to the power 5. If I want to bring take it here, I can, it will be lambda to the power minus 5 e to the power minus b by lambda t d lambda. And here I am thinking, what is A? A is just a constant, okay, and B is also just a constant. A means 8 pi AC, B means AC divided by K. So I put A value over here, B value over here, you will be getting this expression. So I haven't done anything. I have just taken A and B constants. Okay. Okay, this equation is like very known equation, right? Where I have seen this equation. Okay, let me show you. Let me show you. Can you look at this? Can you look at this expression? E lambda d lambda equals to a lambda to the power minus 5 e to the power minus b by lambda t d lambda. Wien's displacement law. Look at this. A lambda to the power minus 5 e to the power minus b by lambda t d lambda. This is Wien's displacement law, and from where I am getting this Wien's displacement law? From Planck's equation I am getting for lower wavelength region. That means this Wien's law is getting satisfied. Yes or no? Wien's law is getting satisfied at lower wavelength region, because I am getting Wien's law from Max Planck's BBR expression. I am getting this Wien's law in case of lower wavelength region. Okay, that means Max Planck's equation is also satisfying the lower wavelength region of the curve. Total energy is also satisfied. It is already satisfied. Now it is satisfied the lower energy portion. Now if I go back and show you, this is Wien's displacement law. It is satisfying this. There are another version of Wien's law, that is lambda max t. That is a constant that gives you this value. Lambda max, I mean maximum wavelength. Maximum wavelength means the possible maximum wavelength. Okay, possible maximum wavelength. What does that mean? Like I am getting this expression. Okay, this one, and if I put a and b over here, constants over here, I will be getting this expression. That is the Wien's displacement law. Now I want to get maximum possible wavelength. Maximum wavelength means, what is the maximum possible wavelength? Maximum possible wavelength. That I have to check. And you know, you have done maxima minima in mathematics. You have done maxima and minima in mathematics. So to get maxima or minima, what you do? Basically you do dE lambda divided by d lambda equals to 0. First derivative, if becomes 0, it becomes maxima. Definitely you check second derivative should be negative to get maxima. But yeah, definitely you will be getting second derivative negative. I am not showing you. I am just applying this concept, maxima minima. So to become maxima, I am thinking that E lambda d lambda will be 0. Now what about the E lambda value? So here the value is, okay, I am sorry guys, I am sorry. Here I am forgetting to put d lambda. Here you have to put d lambda. Okay. Yes, everywhere d lambda is there. So now if I want to put E lambda value, E lambda d lambda equals to this. So I want to get only E lambda value and put it over here. So d by d lambda, then put the value of E lambda. E lambda value is what? And remember, this E lambda value you cannot put from the Max Planck's equation, not this value. You have to put this value for lower wavelength region, and lower wavelength region means this expression or this expression basically, because you have to take this approximation at lower wavelength region. So that's why I am putting this value. So E lambda d lambda equals to this. So I am omitting this d lambda and omitting this d lambda. So E lambda will be only this part. 8 by hc lambda 5, okay, this 8 by hc by lambda to the power 5. Then what is this? E to the power minus hc by lambda kt. E to the power minus hc by lambda kt. Okay. And here whatever lambda you are writing, that is not lambda, that is actually lambda max, because we are doing first derivative. That's the maximum value, that is 0. So now if you solve this differentiation, you can solve it easily. If you solve this differentiation, do you know what you will be getting? You will be getting lambda max equals to lambda max equals to what you should get? Lambda max equals to let me show you something, some values divided by t, or I can just say in this way because I already written this thing. So lambda max t equals to a constant value, or I can say in this way, hc by 5k. Here h is Planck's constant, c is light's velocity at vacuum, k is Boltzmann constant. All these are constant. That means I can write it's a constant. Now if you put all the values of h, c and k, you will be getting this one, 2.9 into 10 to the power minus 3 meter Kelvin. You will be getting this value. If you put this one and this, all these things, you will be getting this value. And I am giving you to check, you know, all these values, I am giving you to check that whether by putting all these values, whether you are getting these expressions or not. It is your homework. Solve it and submit it into the WhatsApp group. Okay, Benzene batch WhatsApp group. Submit it. Check that whether you are getting this expression or not. Okay. This expression again is very known to you, right? This expression is again very known to you. What kind of expression? What is that expression? Look at this. Lambda max t equals to constant 2.8 into 10 to the minus 10 meter Kelvin. That was Wien's law. So I got this expression and this expression at lower wavelength region. Yes, that means, and I am getting from where? I am getting from Max Planck's BBR expression, black body radiation expression. That means from black body radiation expression, I am explaining correctly I am satisfying the Wien's law and Wien's displacement law both. Right? That was done. Now, number 3. Number 3 is about what? Number 3 is about another law I have to satisfy. Which one? Higher wavelength region, Rayleigh-Jean's law I have to satisfy from Max Planck's expression. So I am copying the Max Planck's expression. Third is Rayleigh-Jean's law. And this Rayleigh-Jean's law is applicable at higher wavelength region, higher lambda region. So let me put the Max Planck's expression first, and again I will be dealing with this part. Okay. So what happens? I am doing just mathematics. So don't ask me why it is happening, because this is just a mathematics. I will be telling you why it is happening, but I want to do derivation because like this. I haven't solved this differentiation. I didn't solve this differentiation. You can solve this differentiation and you will be getting this expression. I am not solving this differentiation because this will be just wastage of time. You won't. This live session is already been 2 hours live classes. So I am not doing the derivation. You can solve it at your home and get it. Okay. And you will be getting the same. Check it. Check. I am telling you to check. Please check it. Don't be lazy. Okay. Now, what happens when higher lambda region? What approximation we will be doing? So in case of lower lambda region, we did this approximation that this part is too much higher than this, so I am ignoring this part. I am taking only this thing. In case of higher wavelength region, what happens? I have to deal with only this section. E to the power hc by lambda kt, and you know lambda is very high now. Lambda is very high now means this term will be lower and overall term will be lower. And that's why I will be using some series. You know about Taylor series in mathematics, exponential series, logarithmic series. I will be doing that exponential series like that. And after applying that, I will be getting 1 plus AC by lambda kt. Okay, after getting that series. And I will be putting this value over here. If I put this, what I will be getting? Therefore, E lambda d lambda will be equals to what? 8 pi AC by lambda to the power 5. Then 1 divided by 1 plus e to the power, not e to the power, only AC by lambda kt. AC by lambda kt minus 1. So look at this, plus 1 minus 1 will get cut. Okay. And here it is d lambda. Great. Now if I rearrange it, I will be getting what? E lambda d lambda equals to 8 pi AC divided by lambda to the power 5, then lambda kt divided by AC d lambda, and I am omitting this d lambda and this. I am just omitting. You cannot cut these two. Just I am omitting. What I will be getting? E lambda equals to 8 pi AC divided by lambda to the power 5, and finally lambda kt by AC. Okay. Now lambda to the power 5, it will be giving you lambda to the power 4. AC will get cut. Okay. What I am getting? I am getting 8 pi kt divided by lambda to the power 4. Now again I am taking this E lambda d lambda equals to 8 pi kt by lambda to the power 4 d lambda. Okay, this expression I am getting at higher wavelength region. That means, what is this expression? Can I show you? Rayleigh-Jean's law. E lambda d lambda equals to 8 pi kt divided by lambda to the power 4 d lambda. Explains the black body radiation from higher wavelength region. E lambda d lambda 8 pi kt by lambda to the power 4 d lambda. Yes, I am getting RJ law from Max Planck's expression for higher wavelength region. That means your single expression, Max Planck's expression, this expression explains Wien's law at lower wavelength region, explains RJ law, Rayleigh-Jean's law at higher wavelength region, and explains Stephan-Boltzmann law to calculate total energy. That means these law is satisfying lower wavelength region of the plot, these law is satisfying higher wavelength region of the plot. What does that mean? It means these two laws are actually satisfying, this total Max Planck's expression is actually satisfying the total plot, not only this part, not only this part. Only one single law, only one single expression is satisfying the total law. That is Max Planck's black body radiation expression. Understood? Say, lot of mathematics are there, but at the end of the day, I am getting my results. Got it? So if you understood it, write you in the comment box. Please write you in the comment box if you understood it. And if you are late, please do watch the video from the beginning. You will be getting everything. Now, everything is done. That means this plot has been explained perfectly by only one single expression, that is called Max Planck's expression. So from Max Planck's expression, this law has been explained successfully. Okay. Now I want to add a simple single logic. Okay, that discussion of this class has been done. That we have discussed this. Let me show you. We have discussed this black body radiation perfectly, and to explain the black body radiation, we need quantum theory, not classical theory. Classical theory won't help us to explain the total black body radiation by only one single theory. But one single quantum mechanical theory can explain the total black body radiation. That means Max Planck's theory is correct, and we are entering into the quantum theory, quantum mechanics. Got it? Now what is the, in the next class I will be talking about this photoelectric effect. Photoelectric effect, and this effect is present in your syllabus. And nothing to worry, I already discussed this thing whenever I was discussing the Bohr theory, spectral lines of atoms. I already discussed these things. So in the next class we will be talking about this photoelectric effect. But before I leave, I want to show you something regarding Rayleigh-Jean's law. This Rayleigh-Jean's law, okay? Rayleigh-Jean's law, this one. That thing is called ultraviolet catastrophe. Ultraviolet catastrophe. Okay, that thing is called ultraviolet catastrophe. What is that? So basically, ultraviolet catastrophe is the phenomena that I will be getting from Rayleigh-Jean's law. So from Rayleigh-Jean's law, if I want to calculate total energy from RJ law, suppose that means E I want to calculate, E lambda I want to calculate. How to do that? I know this is my Rayleigh-Jean's law. Or if you want to check the same thing from the previous one, you will be getting it. This is your Rayleigh-Jean's law. 8 pi kt by lambda to the power 4 d lambda. Let me write it. So E lambda equals to E lambda d lambda equals to 8 pi kt by lambda to the power 4 d lambda. So now I want to calculate total energy, right? How to get total energy? To calculate total energy, I have to, like, E lambda total will be what? So again, total energy means from 0 to infinity wavelength, 8 pi kt divided by lambda to the power 4 d lambda. Okay. Now if I calculate this, if I put this thing, E lambda total equals to what? I have to do the integration. So 8 pi kt, these are constants, so I am bringing this out from the integration. Then I am getting 0 to infinity lambda to the power minus 4 d lambda. Now if you solve this integration, you will be getting what? 8 pi kt, it will give you lambda to the power minus 4 plus 1 by minus 4 plus 1, 0 and infinity. And if you solve this, do you know what you will be getting? Let me show you. 8 pi kt 1 by minus 1 by 3 lambda cube 0 to infinity. That gives me, if I put this thing 8 pi kt minus 8 pi kt 1 by 3 into infinity minus 1 by 0. That means 1 by infinity means what? 0. 1 by 0 means what? Infinity. And I am multiplying this minus with this and this. It is infinity, so it will get infinity, it will become 0. So plus 0 minus 0 doesn't give you anything. So 8 pi kt, then multiplying with this negative, it will become 0, and negative will become positive. 1 by 0 means infinity into infinity. That gives you infinity. That means if you look at this expression properly, total energy is becoming infinity. Total energy means 0 to infinity wavelength in this region, total energy is becoming infinity. How is that possible? How is that possible that our total energy is becoming infinity? It is impossible, right? So how to deal with this thing? So these phenomena that total energy is becoming infinity at any temperature, except T equals to 0. This phenomena is called ultraviolet catastrophe. Okay, so what is ultraviolet catastrophe? So why I am telling you that except T equals to 0. So at any temperature, any positive temperature, whatever your temperature is 10 Kelvin, it doesn't matter, 20 Kelvin, 100 Kelvin, 200 Kelvin, 400 Kelvin, whatever your temperature is, you are multiplying with infinity. That will give you infinity. That means your energy will be infinity. Whatever your temperature, suppose 1 degree Celsius, that gives you infinity energy. Is that possible? No, not possible. That means your Rayleigh-Jean's law cannot calculate the total energy. cannot calculate the total energy. If you are calculating total energy, that gives you a like weird result. That is your that phenomenon is called ultraviolet catastrophe. But whenever T equals to 0, look at this. Whenever T equals to 0, absolute temperature is 0. If you put 0, 0 multiplies anything, that gives you 0. So except T equals to 0, at any temperature you will be getting infinity. At T equals to 0, everything energy will be 0. Okay, that means except T equals to 0, the phenomenon is called ultraviolet catastrophe. That is the thing that I wanted to discuss. So that's all about this thing. That's all about this basic quantum theory. In the next class, I will be talking about photoelectric effect. What is photoelectric effect? Photoelectric effect. In the next class, we will be talking about this. And based upon this photoelectric effect, Albert Einstein got Nobel Prize in Physics. So remember, this effect is very important to understand. Okay, then we will be moving forward to the wave mechanics, that is de Broglie theory, Heisenberg uncertainty principle, then Schrodinger wave equation, derivation, quantum mechanics, operator algebra, operators, then how to deal with different kinds of orbitals, how orbitals concept is coming, everything we need to understand from the basics, and that we will be doing in future. So this chapter will take a little bit more time to understand. Other chapters won't take a lot of time. It will take 2 or 3 or 4 classes maximum. But this chapter is very important to understand. That's why it will take a lot of time to complete. Fine. So meet you in the next class. Till then, bye bye.